So, because it was
The holes. Oh, that's fine. That's totally fine. I'm not trying to say you're right and wrong. It's your vote whether you think it is or not. There's a conservative way to deal with outliers, and there's the it is bell-shaped enough way to deal. There's a slight, that's a pretty conservative way too, but the even more conservative way is outlier ID number 2. But I want to talk about what Kelly just said. Yeah, it's a fairly wide curve. I mean, with a bell curve, you guys have probably gotten used to seeing it kind of drawn like that, where there's more in the middle, less in the tails. But bell curves, the only thing they have in common is 100% of the data is under it. It can be extraordinarily flat and very, very wide, or extraordinarily tall and very, very skinny. It depends on the standard deviation. That's one way of measuring variation in a curve, is how wide and how tall it is. So good, and more on that to come, my friend, more on that to come. But if you said, no, I don't think it's bell-shaped enough, or I'd like to collect more data to see if it's bell-shaped, that's totally fine too. So let's look at outlier identification method number 2. I want to ask you about it though. Do you remember yesterday? I said yesterday, I meant Thursday. We did that little in-class quiz with the snowfall data. And at the very end, when all those beautiful box plots were up, and I said, I think I can find out which groups had at least one outlier. And I went, yeah, no, yeah. And I was right in almost every case, right? Is that magic?
No.
Of course not, you know me by now. Was I doing that? Was I doing that? Hell no, I was not. Don't give me that much credit. I can't calculate averages in my head, and I definitely can't calculate standard deviations in my head. So what the hell was I doing? Zach?
Check the boxes, times 50%. Seeing if it came outside of the distribution bars.
Here's what I was doing. Everybody make a box plot on your histogram right now. So in other words, you already have the histogram. Up here, put a box plot, like we did on the quiz. Leave plot 1 on, is what I'm saying. Leave plot 1 on, turn plot 2 on as a box plot. Mine's all ready to go from, yours might be too from Thursday, actually, I think about it. Mine's already ready to go. It's calling from L1. I think I need frequency at L2 though. Other than that, everything's ready to go. Box plot. Yeah, good. And then you should just press graph. I think you should press graph. Should pop right up there on top of it. Fair. So turn, good, talk to each other, very good. Everybody getting successful box plots? Sean, go ahead.
How come our whiskers stopped before our last data point and that's not considered an outlier?
How come say that again.
Our 100 percentile whisker.
Yes?
These are not.
Oh, this is Lydia's question. The number 185 is actually right there. That's one, remember how I have to make that X max 5 more? So, because I have to make room for that last bar. That's 185 right there. That's technically where that whisker is. Just like Sean, there's 145. I don't know what this vertical line is here. Let's get rid of that. Let's make this, I don't know, 10. Yeah, that's a little bit better. So Sean, that answers your question, I hope. It's because the TI can't graph a width of 1 in most cases. It needs to have a width of at least 2 or 1.1. So don't worry too much about that. Sean's point is a good one. Technically speaking, this bar should be lined up with that whisker because they're both the max values. It's just a limitation of the technology. Thank you, sir. Very good point, very good point. I love having the histogram up with the box plot. I love that because you can see where the average is with respect to where the median is. Yeah, and you can see that you have an idea of spread. You have an idea of spread. These are a little more spread out than these because that whisker's a little bit longer. 25% of you voted here to here, 25% of you voted here to here, 25% of you voted here to here, very tightly clustered in here, which corresponds to a pretty tight clustering in here. 25% of you voted right here. Everybody getting success with their box plots?
No, I can't get this done.
Oh, okay, let's see if we can figure it out. All right, good, not a problem. Let's get started. That's step plots. You got plot 1 on, you got plot 2 on. Air stat. Okay, so I'm guessing it's the window. Let's just press zoom 9, which is the default. Zoom 9 will always. This should be L1, L2. Your data's in L1, your frequencies are in L2. Let's make sure that one's good. There it is. There it is. I wonder why. Yeah, you can't grab the frequencies with respect to the frequencies. Well, there we go. That's right. Gotta figure it out now. So now, the question is, what trick did I do in class on Thursday to figure out where the outliers were? Well, here's what I did with my, did I show you with my hands what I was doing? I went like this. I figured out the middle of the box. This right here, this distance between Q1 and Q2, this is Q1, yes? This is Q3. The distance between Q1 and Q3 is called the interquartile range. Interquartile range. Why? I don't know, it just is. Quartiles. Like an interstate highway goes between states. Interquartile. In our case, that number, I don't know what that number is. I'm going to figure it out. Q1 is 155. That means 25% of you guessed I was lighter than 155-ish. Q3 is 170. 25% of you also guessed I was more than 170. So the interquartile range is the difference between those two numbers, 155 and 170. Now, what does that number tell us? I told you that 25% of you guessed I was lighter than 155, and 25% of you guessed I was heavier than 170. So what does that range demarcate? What does the box demarcate? The 50% of you in the middle that guessed in the middle. So you have to think about that range kind of like a standard deviation if you don't want to use a standard deviation. So this is where we're getting away from outlier method number one that relies on bell-shaped data. This gives us a baseline spread measure to work off of. A baseline spread measure to work off of if you can't arguably say your data is bell-shaped. If you can't arguably say your data is bell-shaped. So if you're like, I don't think it's bell-shaped enough, this still tells you 50% of your data is between those two values, 15 units wide. So it's analogous, if you will. It's analogous to the standard deviation, but you could also use this if you don't have bell-shaped data. Fair enough? So what I did in class yesterday was, I didn't actually do the numbers. I just went like this, and then I increased it by 50%. So I made it 50% bigger. Now, if I do that down here, do mathematics, and I was going, why did you do that? Hold that question, my friend. That's a great question. Hopefully I looked at your thinking, right? Why? Good. Very, very good question. You then increase it by a factor of 50%. 1.5 times that IQR. IQR is just an acronym for interquartile range. Increase it by 50%, so 22.5 pounds, I believe. Always check my math on this. That's analogous to when we go out, how many standard deviations over there? 2 standard deviations. So the question then, of course, a logical question, as Anna just came up with, is why use 1.5? I have no good answer for that. I have 0 good answer for that, other than it's the one that gets used. That's a terrible answer. That is a terrible answer. I'm not trying to say that it's a good answer. I'm saying that's the one that is used. Much like, why do we use the p-value of 5%? Because we do. Why do we drive on the right side of the road and use the English system of measurement? Because we do. I mean, there are historical reasons for those things too. And there are historical reasons for this. I don't know the history behind it. So then, remember what I did after I did that yesterday? I went like this, and then I took that range, and I stacked it here, and then I stacked it here. So I took that 1.5 interquartile range, and I stacked it on top of Q3, and then I stacked it below Q1. What was I looking for? What was I? Go ahead, say it nice and loud. Outliers. What would be an outlier? If I stack it here, where would the outliers be on the right side?
Right.
Over here somewhere. And if I stack them here, where would the outliers be? Left. So after you've done that stack of the IQR, you look. If you're looking for like a procedure, you check. Now this is what mathematically it's going to look like. Check for outliers Number one, above. This is going to look like Greek, but it's not. Q3 plus 1.5 IQR. That might look like Greek, but it's not. Q3 plus 1.5 IQR is the same thing as here. This would be Q3 plus 1.5 IQR, wouldn't it? Stacked 1.5 IQRs above Q3. Do we have any outliers out there? Did anybody guess above that number? I don't even know what that number is, but I know nobody guessed it because it's past my highest point of my box plot, yeah? Now, could we calculate that? Of course. We know that Q3 is 170 plus 22.5 is 192.5. Nobody guessed that I was 193 pounds or 200 pounds or 210 or anything like that. So nobody guessed that high. In other words, there were no high outliers. No high outliers. Any low outliers? It doesn't look like it, does it? Because that would have to be down here. This would be Q1 minus 1.5 IQRs, yes? Yeah, it's there. It doesn't look like it. So we check above Q3 plus and below Q1 minus 1.5 IQRs. Now, mathematically, we can calculate that, right? We can say, okay, 155 minus 22.5. 132.5, I think, 132.5. Nobody guessed that I was 130. Nobody guessed that you were close to that. The lowest guess was 145. Nobody got close to 132.5. Therefore, you guys don't have any outlier guesses by that method either. That's it. Do you see the difference, though, in the range that's allowed for the two of them? When you assume the bell shape of data, it only goes from 145 to 185. When you allow for the variance around the outliers based on quartiles, it goes from 130 up to 190. Much, much wider. In general, that is the case. In general, that is the case. I don't have a good answer, Anna, as to why 1.5 is used. But when I was in school, and this is going back 20 years now, it was 3 standard deviations and 3 times the interquartile range. So in other words, this wasn't 1.5, it was 3. So instead of 15, it was 45, not 22.5. And 3 standard deviations went down to 135, went up to 195. Why have these things changed? I don't have a good answer for that. They just have. They have changed. It's kind of inexcusable, but they have changed. So it's rather unfortunate that they have. I don't know why. I mean, it's just that's what's used. If you oh please, Stephen.
I think it has to do with the accuracy of the data you collected nowadays.
I like that answer a whole lot, Stephen. I like the answer to that a whole lot, and I'd like to augment that with it also depends if you're making inferential conclusions on which way you can accept being wrong more. Could you accept a false positive or a false negative more? And that's how you can actually decide how many standard deviations you should use. More on that toward the end of the course. I like what you just said, and I think it tags up nicely with what I just said too. But more on that in about 3 weeks. You're getting actually into 244 right there, which I like an awful lot. Cool? So your call. They won't always agree with each other. Sometimes one data set might, one approach might have an outlier and this one might not. That happens. That happens. But it's your call as to which one of these. You won't have to do them both. That's kind of silly. Just pick whatever one you think. You can always default to this one. You can always default to this one, which would be out. Let's call this something, shall we, so we can talk about it. Let's call this outlier ID method number 2. Outlier ID method number 2. And we'll call this the IQR method. There we go. What was the condition on outlier ID method number 1? We had to have? What is the condition on outlier ID method number 2? It's a trick question. There is no condition. You can do it on any set of data you want to. It doesn't have to be bell-shaped, but it can be. Did you notice how those of you that said this was bell-shaped, we still ran on this? We did, didn't we? Yes, we did. So it doesn't matter. There's no condition on this, which is another reason I think it's frequently used. Frequently used because any data set, no matter how skewed, no matter how off things are, you've got outliers. So now, hopefully you see, let's tie it back. I have 2 more data sets I want to analyze. You can see now why certain test scores on your exams were outliers. Let's go back and look at them again.